Hello everyone, this is Cody Jackson for Codamom, and we are continuing our Practical Information Technology series. This time we're going to take a look at basic direct current theory, and this is going to be foundational for a lot of things in the future because obviously electronics requires electricity, and the electricity that we use is direct current. So while this may not necessarily mean a whole lot to you at this moment, it will apply to certain things such as transistor theory, digital circuits and stuff like that we'll be talking about later. So I'm going to start with some fundamentals of electronics and electrical theory. Now, I have the title in here not completely accurate because the information that I put in here is more or less layman's terms, and it's not the correct academic or technician terminology and stuff like that. And that's really just to make sure that you understand what's going on, and it's not book accurate. So if anybody does have some electronics background, please don't flame me. I know that the material I'm presenting here is not completely accurate, and that is on purpose. So, atoms have protons, neutrons, and electrons. You should remember this from basic school. Stable atoms have the same number of protons and electrons. They're unlikely to release those electrons because they have a very strong valence bond. The electrons that we care about in terms of electrical flow are on the outer shell. So if you remember the Bohr's model, basically it looks like a bullseye. In the center you have your protons and your neutrons, and then you have different valence layers of electrons, and it's all based on that. We don't care about anything except for the outer shell electrons. If those electrons in the outer shell are less than the number of protons, it is easier for those electrons to become excited. If they become excited, they gain higher energy, and they are more likely to leave that particular atom and jump to another atom. So electricity flow is when you have a large number of these electrons moving from atom to atom. Conductors, it's incredibly easy for the electrons to move from atom to atom. And so when an atom moves, it leaves a hole in its parent atom, and that hole is then subsequently filled by the electron from another atom. And so that's how conductors move electricity along. So a copper wire has very easy flow between the different atoms as their electrons flow between holes, basically. Semiconductors require a moderate amount of energy. They can act either as a conductor or an insulator based off of the circuit conditions. And we'll talk about semiconductors later because that's basically what makes a computer work. Insulators are extremely stable. There's the same number of electrons as there is protons, and therefore it's almost impossible to cause those electrons to be excited and jump to another atom. Hence, insulators are used to prevent current flow across a particular thing. Plastic-coated wires, plastic is an insulator. It doesn't allow electricity flow, and so they're very common for that. Now, recognize that if you have a high enough voltage, you're going to cause those electrons to excite regardless or not of the normal conditions, and so you will eventually burn through the insulation as the electrons try to flow through that. Voltage is the potential difference between 2 points. A potential difference is basically how much work is available for a current to do something. And so I have the example in here of a ball in a tree. The higher the tree, the more work is available for that ball to do. Whether you want to put it on a pendulum, whether you want to tie it to a rope and automatically pull an object up, whatever the case may be, the height equals the potential kinetic energy. Same thing for voltage. A higher voltage means a higher potential for work to be done. Voltage doesn't know anything about the conductor path. It is only about the potential of work. A high voltage doesn't necessarily mean high current. And current is what can kill you. And so the obligatory safety notice, when you're working with electricity, current going across your heart in excess of, I believe it's 100 milliamps, 100 milliamps will kill you. So if you have a circuit from one fingertip to the other fingertip, that path, it goes right through your heart and you will die. At low voltages, if you have a high conductivity of your body, so say you're wet, then your resistance is low, and that means it's easier for the current to flow through you, and that's why people die when they're in swimming pools or water locations, boating or something like that, and lightning strikes. They're already wet, so their resistance to current flow is much lower than it is normally. Current is the measure of the electrons flowing through a conductor that actually does work. So without current flow, work does not get done. Lights don't light up, motors don't turn, batteries don't charge, stuff like that. So if you have a low resistance, you have a higher current. If you have a short circuit, you have a direct path between your voltage potentials, between the high potential and the low potential. And it's just going straight through that, nothing is stopping it. So, short circuits are bad for circuitry. Obviously, it burns them out. But you, as a person, can become that short circuit if you're not paying attention to what you're doing. Even if you're working on something that's low voltage, for example, a car battery, it has the potential of a lot of amperage, a lot of current coming out of it. So, an average car battery is 12 volts, but can generate 3.5 amps. And I said 100 milliamps can kill you. That's 0.1 amps. So you basically have in a car battery, what's that, 350 times the current necessary to kill you? But it's only 12 volts. What I'm trying to get at is the rating of voltage is not correlative directly to the current that can be generated. You can have a lot of voltage, but if you have a big enough resistor, you're only going to be getting, milliamps out of that circuit. Resistance is opposition to the current flow. So that could be a workload, such as a lamp, a motor, charging a battery or something like that, or a traditional resistor, which is basically just a carbon tube that inhibits the flow of current and basically just dumps that heat or jumps that current flow as heat. So resistors get hot. If you ever look inside power supplies, you'll see fairly large resistors in there, typically ceramic, because they can get incredibly hot. I've actually seen ceramic resistors crack because of the amount of current that was going through them. On a normal circuit board, though, you'll see incredibly tiny surface mount resistors on there that combined dump a lot of current as heat. But because we're talking about 12 volts or less on a motherboard, typically 5 volts or less, and even smaller amounts when you get to actual CPUs, the amount of resistance required to get a circuit working correctly is very minimal. Power is the work done in a given amount of time, and that's measured in watts. I skipped this. So voltage measured in volts, denoted by an E when you're looking at circuit diagrams. Current measured in amps, denoted by an I in circuit diagrams. Resistance measured in ohms, noted by an R, and then power measured in watts with a W. Some useful formulas. Ohm's law. Resistance is voltage divided by current. Or you can swap those around. Current is voltage divided by resistance. Voltage is current times resistance. It's basic algebra. So you can use any two factors to calculate the third one. If you know the voltage and you know the resistance in the circuit, you can calculate how much current is going through that circuit. Generally speaking, when you are working with circuits, you don't have the opportunity to break into the circuit and physically measure the current flowing through it. But you can touch points and measure the voltage between a particular point and ground. Ground being a reference. That's going to have 0 volts, but that's going to be your reference point. And there's a lot of different things you can talk about. You can talk about earth ground, chassis ground, stuff like that. For our purposes, a lot of what we're going to be doing is chassis ground because we are physically working within a chassis, a computer box. The box is a chassis. On your car, the chassis of the car is the ground. So the negative terminal of your battery is actually connected to the car frame. That's why when you jump start a car, you put the positive terminal onto the battery, you put the negative terminal onto some part of the car's chassis. You don't directly put it onto the battery because then you can cause things to explode. Power is current times voltage, the pi formula. And since we already talked about Ohm's law, if you don't know current or voltage, but you know the other two, you can substitute those combinations into the power formula and figure out what the power is based off of resistance and stuff like that. Alright, so here's a simple example. A 100-watt lamp connected to 250 volt power supply. Calculate the circuit current and the lamp resistance. So, walking through it, we have, let's get a little pointer. So, we have our power formula. We're going to calculate power. Sorry. We know what our power is. It's 100 watts. So, moving the formula around, we want to solve for current. Current is power divided by voltage. So 100 watts divided by 250 amps gives us just under half an amp, 400 milliamps. The lamp resistance is voltage divided by current. So voltage was 250 volts. We know what the current, we just calculated, it was 0.4 amps. And so we come up with a calculation of 625 ohms for that lamp. Alright, so I want to jump over to the electronicshub.org just to explain the stuff a little bit better using some graphics. So here is an example of what we were just talking about. 100 watt bulb, 250 volt battery power supply. This is just a circuit breaker or switch or whatever you want it to be in terms of powering this bulb. This just gives you an idea of what it is that we're talking about, plus how a circuit diagram looks. So a battery is this symbol. Technically, this is just a battery cell. A battery is two or more of these together, but you'll most commonly see it as just this. You'll commonly see resistors in this form, which basically just shows that your current is coming in one direction and then it has to take a very circuitous route to get to the other side, and that is your resistance to current flow rather than a straight pipe. This just means it's a variable resistor. This is also a variable resistor, and sometimes you may see this arrow coming off to another circuit basically tapping off of the resistance. So say you had a 100 ohm resistor across this entire thing, but if you put it halfway, that's only 50 ohms. I don't want to get into the details, but they have things called rheostats and potentiometers that allow you to dial in that resistance. When you're working with, say, a stereo or something like that, especially if it's analog, meaning it's not digital, you actually have dials on there. Those dials are actually potentiometers that will go in and adjust the resistance coming out, and that is what actually affects the volume or the frequency or whatever the case may be. Let's see what else we got. So here's a good point. Do not get hung up on this. Current flow. Current flow is from the negative terminal of a battery or power supply to the positive. That the electrons as negative charged particles are coming from the negative side to the positive side. Due to some historic issues, is basically 50-50 guess when they decided how current flowed, and they chose wrong. So conventional current is positive to negative. That's why you'll see diodes having an arrow pointing in the direction of current flow. Technically it's wrong, but it doesn't matter. It actually does not affect anything when you're looking at circuits. I only mention this because if you're looking at a technical diagram for electronics technicians and it talks about electron flow, especially if it has a directional arrow like this, like say through different pathways, it'll be coming from the negative side of the battery or the power supply through the circuit. If you're talking to an electrical engineer or somebody who is an electrician, they'll talk about conventional current coming from the positive side. It doesn't matter in your calculations. It's just a convention of how those currents are demonstrated. We'll talk about AC and DC currents in a second, so I'm not going to talk about those right now. You'll often see power supplies shown as either a battery, like I said here, with a positive and negative terminal, or as a black box power supply. If it's a DC thing, then you'll have a positive and a negative on here indicating where the current is coming from. If it's a alternating current, then you'll have a sine wave in here. This right here is what I talked about. The correct way to show a battery is to have multiple cells in it. You may or may not see that in actual schematic diagrams. Coming back up to the beginning, here is where we're talking about the atoms and the electrons that are connected to them, and the valence bonds and all that stuff. This is all physics theory. I'm not going to talk about it. You're free to look more into it, but it's not important for what we're talking about. This is a little bit more important in that a conductor is the outer electron, and it only has 1 to 3 valence electrons. So if we assume that we have 6 protons in here, then we need to have 6 electrons for it to match. And in an insulator, we have that. So it's very difficult for these electrons to break free because they are sharing the contact current, for want of a better term, between the protons and the electrons, basically to keep this outer shell balanced. If you have fewer electrons, it's easier for those electrons to gain energy and leave this atom. So if we had 6 protons in here and we only have a single atom or a single electron circling it, this single electron has the equivalent of 6 protons worth of energy available to it. So it doesn't take a whole lot to excite it and cause it to jump out of that valence bond. Whereas over here in an insulator, they all have an equal amount because they are 1/6 of the entire amount that's there. Again, not completely accurate, just trying to get the point across. Electricity types: direct current, alternating current. Direct current flows in one direction, from a high voltage to a low voltage. It was the earliest discovery. You can take a look at the history. You can look at the different battery piles that were created and things like that. It is most useful in electronics. You will hardly ever see alternating current within an electronic device unless it's doing something RF related, modulation, things like that. But in terms of actual power within an electronic circuit, it's primarily going to be DC. And even if you have AC coming in, at some point it's probably going to be rectified into DC current. DC is not good for long distance power transport. So the power lines that you see on the side of the road, those are carrying alternating current because it's just cheaper that way. Examples of DC: batteries, DC power supplies, solar panels. Again, a lot of the stuff that you associate with electronics. AC goes back and forth in direction, it alternates directions. And if you put it into an oscilloscope, so you basically track voltage over time, you see a sine wave. It has to be rectified into direct current before it can be used within electronic situations. Talked about how it's cheaper and easier for power line transmissions, and you'll see it in AC power supplies, generators, power lines, your house outlets, stuff like that. If we jump back to electronicshub.org, DC current. In this example, it's flowing from the negative terminal through the resistor to the positive terminal. Alternating current, as I said, it has a sine wave showing that it's an AC generator, and the current will go in one direction, and then the next cycle it will go in the other direction. So if you equate it to a sine wave, over time you'll have positive voltage, you'll have negative voltage. If you did not look at this over time, it would be a circle, positive to negative, positive to negative. And that's really all a generator does. Spins in a circle, and the voltage comes out from that thing. So it spins in a circle, and the only reason we see a sine wave is because we are marking the position of that circular movement over time. So that's it for this video. I hope it wasn't terribly boring. I tried to give enough foundational stuff that you have an understanding. When we start talking about digital circuits, you'll know where we're coming from, and the terms won't be as frightening to you. So we talked about basic atomic theory of electronics, discussed how conductors, insulators, and semiconductors are different in terms of their ability to allow electron flow. We talked about voltage, current, resistance, and power. Discussed the useful formulas of Ohm's law and the power equation. We use those to calculate a simple DC circuit. And then we talked about the differences between AC and DC electricity. Not listed on here was be safe when it comes to electricity. It can kill you. It doesn't take a whole lot to kill you. And even low voltage sources can have high current available to them. Like I said, a car battery, 12 volts, 3.5 amps. You only need 0.1 amps across your heart to kill you. So next time, we're going to jump into basic digital circuits, nothing heavy. We're basically just going to take our DC discussion that we talked about in this video and show how it applies to transistors and how those transistors help create the basics of how computers work. So Regardless of whether you found this boring or not, I hope you found it useful and educational. As normal, leave comments in the comments of the video, critiques, anything like that. Until next time, have fun, keep learning. Bye.